Good afternoon, everyone. I'm Yue-Yang, a PhD student from USTC. It's a really pleasure to be here at QCrypt to present our recent experiment work on the quantum channel purification. This is a joint work with Zhenhuan Liu from Tsinghua, Zhenyu Chai from Oxford, and Ray Zhang and Professor Yao Chen from USTC. As we know, quantum networks are fundamental for quantum cryptography and multi-party quantum computation. In these networks, quantum channels link up quantum processing units that are spread across different locations. However, as networks get bigger, noise in these channels becomes a problem. It influences the transmission of the quantum information, so finding ways to suppress this noise is important. And now, different methods have been proposed to deal with noise in the quantum networks. The two primary approaches are the entangled purification and the quantum error correction. Entangled purification uses copies of noisy, low-fidelity entangled states to produce a higher fidelity one. However, the state conservation lowers the overall generation rate, and the quantum error correction suppress noise by increasing the system size through complex encoding and decoding operations. It only needs one-way communication and can be easily expanded to any input state. However, implementing quantum error correction in an optical system remains challenging. And to ease the difficulties of these two approaches, we proposed the channel purification protocol. It uses several noise channels to generate this noise one. And let's take a two-channel circuit as an example. This circuit has three registers. The main register, which starts with the input state, and an auxiliary register in the maximally mixed state, and the control register in the plus state. And between the two control swap gates, there are two noisy channels we need to be profiled. And they can be represented as the sum of Pauli operations via Pauli toiling. And at the end of the circuit, one measures the control qubit in Pauli X spaces and discards auxiliary register. And if the measurement result of the control qubit is the plus state, we keep the main register as the output of the purified channel. And now compare the two channels. The P0 is the probability of the target noise component. If it is the highest probability in the initial noisy channel, the purified channel always performs closer to the noisy channel. And additionally, even though we select the control qubit measurement, we can also utilize the discussed data like a virtual state purification, QEM method. And by evaluating the difference in the control qubit results plus and minus, we extract a virtual purified channel, maximizing the use of the all experiment data. Our protocol has several key advantages. As you can see in the figure on the left, the entangled purification targets the enter state and requires all the users to perform the local operations and classical communication. This makes it hard to scale up in a larger network. However, the channel purification can target on the noisy channel and conceal the auxiliary qubit instead of the previous entangled states. Compared with the quantum error correction, the channel purification can be applied on a wide range of noise levels. It is friendly to the current device, and we developed a way to implement a control swap operator used in this protocol. And to implement the protocol, we encode photons in both polarization and the spatial degrees of freedom. And here, the spatial state 0 and 1 means the photon is in the top or in the bottom layer. Based on that, we designed a new optical device. It transmits top layer's photons and reflects the bottom layer photons. And this work works on the spatial modes, just like PBS work on the polarization. So we call it a spare bin slitter, or SBS for short. With SPS, we can put the protocol into a linear optical system by expanding the original circuit to a 4-qubit one. And in this new circuit, we use the bare state 5 plus as a control qubits instead of the plus state in the original circuit. And the 2 photons, we color the red and orange, carry the input and the accelerate qubits in their polarization degrees of freedom. And their spatial modes are entangled as the bare state. And this setup allows us to perform a control swap-like operator after the photons pass through the SPS. And to make sure we get the right outcome, we measure both spatial modes using the X basis. And the measurement results are then divided into the 2 groups, plus and minus, corresponding to the measurement result in the original circuit. This slide expands our experiment setup, which we have split into the 3 parts, and the initialization, the purification, and the measurement. First, in the initializing part, we use an SPDC source to prepare the entangled sphere qubits. Then we form a maximally mixed state using a Fourier deflection operator by seek crystal, and form the important state by rotating wave planes. And the next purification, this is where the SPS performs the main operators. And finally, the measurement, we place the beam splitters on both sides to act as the spatial hardenment gates. The interference visibility at the beam splitters in the spatial degrees of freedom dominantly shows how efficient the purification is. And in our experiment, the visibility reaches 0.936 when 2 poly rotations were identical. And such high visibility is key to making the protocol work well. And we run process tomography on the 2 initial noisy channels and the purified channels to show how well the purification works. For each channel, we use 12 different measurement setup with different inputs and measurement bases. And in this test, we pick up the 2 different noisy channels. The channel 1 is which makes the identical channel with bit flip errors, and the channel 2 with the phase flip errors. And you can see the tomography results on the right. The value here is the absolute value. And now look at the IM-X-ray element. This tells us how much of the channel is noisy. And after purification, this element's value increases. And by using the virtual purification, the value is raised to 0.9 while keeping other noisy elements very small. And to be more general, we also tested using depolarizing channels for both initial channels. To measure the performance, we used the average fidelity compared to the ideal noise channel. Now, look at the finger on the right. The blue line is the ideal value of the initial channel, and the red one is the purified channel, and the yellow is the virtual purified channel. The error bars here are really small, or below 1/10,000, so we left them out. Both purification methods always achieve a higher average fidelity than the initial channels, and this result shows that our experiment setup works well under different conditions and suppresses the noise effectively. And our method can work in many situations. For example, it can distribute entanglement states in the quantum networks. And we look at the simplest case with the two users. Suppose the channels to Bob suffer from a strong noise due to the element or the device problems. We use our protocol to provide it and share a higher fidelity entangled state between Alice and Bob. And here is the specific setup we used for the entanglement distribution. We extended the initialization part to prepare a distributed bare state. The 3 photons from the 2 SPDC sources become entangled in their spatial degrees of freedom by overlapping them on the PBS1. And we then interference the photons on PBS2 to prepare the distributed Beer state. And the purification part and the measurement part are still the same. We measure the fidelity between the distributed states and the target Beer state. In the left finger, the dashed lines shows the simulation results. They are based on the initial tomography data when not introducing any noise. And for different noise levels in the initial channels, the purified channels always distribute states with a higher fidelity. And notably, for the initial channels marked here, the tomography showed the transmitted states were separable. But after using the purified channel, the distributed state still had entangled with a fidelity over 0.5. This shows clear. Channel purification helps the distributed state stay entangled, even when there is so much noise that the entanglement would normally break. And here is the take-home message. We demonstrate the first experiment implementation of channel purification on a linear optical platform and applied it in the entanglement distribution. And finally, let's go over some future directions. First off, the joint spatial measurement on the both beam splitters basically act like a Homedo interferometer. It naturally has a reference data and handles the phase flexion really well, which makes it a great fit for the long-distance communication. And next, we are looking to improve the protocol by adding extra noisy channels, like the multi-channel purification, to get a better result. And finally, our protocol is compatible in the quantum circuit, so it would also be useful to combine the channel purification with the other protocols, like entangled purification and quantum error correction. And that's all. Thank you for listening.
It's a very nice talk.
Thank you for the very nice talk. So I had a question about the controlled swap gate. What's the probability of success for the operation?
I think when this two photon count is I think it's always success.
So it's a deterministic gate.
Yeah.
Okay.
I think the really challenging is the interference on the beam splitter.
So, sorry, just a follow-up question. That means there's no post-selection that's needed in order for the operation?
Yes, it's the post-selection. We should post when they post it to the plus state.
Okay, yeah, I might follow up on this separately. Thank you.
Any more questions?
Thanks for your excellent talk. And my question is, in your experiment, you use 2 qubit and 3 qubit entangled states to show the advantage compared to the traditional heralded entanglement purification, right? So my question is, does that mean if there will be more advantage if I add more qubits? For example, if I use 4 qubits or 5 qubits entangled state, will there be more advantages?
Yes, I mean the multi-channel purification. We use more than 2 channels to purification. Yes, that's the next we wanted to do.
Okay, thank you.